Hi everybody. In this section we're going to finish chapter 1, and this section is called Experiments and Observational Studies. So let's get started. Alright, so first thing we want to talk about is two definitions, association and causation. And these are ways that studies can show a connection between two variables, and there's two different types of connections. Right? The first one is just an association. That means that the values of one variable tend to be related to the values of the other variable. It just means that the two values occur more frequently together. And then there is a different kind of association called a causal association. It's not a casual association, it's causal. And the two variables are causally associated if changing the value of one variable influences the value of the other variable. So causal association is also just sometimes shortened to causation, or we call it cause and effect association. All of these things mean the same thing. Causal association, causation, cause and effect all mean the same thing. So what's the difference between these two things? Well, an association just means that two things are happening together. So an easy example of two associated variables would be height and weight. Generally, people who are taller are also heavier, so there's an association between height and weight. But height and weight are not causally associated, because you can't change somebody's height, right? And changing somebody's weight won't adjust their height. So it's just an association. It just means taller people are generally heavier. So these causal associations are when one variable is actually creating an effect in the other variable. So let's just do a quick example of this just to see how it works. Every day we see headlines such as wealthy people are more likely to lie, cheat, and steal. Daily exercise improves mental performance. And among college students, no link found between number of friends on social networking websites and the size of the university. So which of these claims are attempting to show association, causation, both association and causation, or neither one? Right, because there's four things that could happen, you would think. All right, so let's look at the first one. Wealthy people are more likely to lie, cheat, and steal. Is that association, causation, or both or neither? So it turns out this one is just association. And the reason there's no cause and effect relationship here is that you can't change somebody's wealth to see if it makes them lie, cheat, or steal. And you can't tell somebody to lie, cheat, or steal and see if it changes their wealth. Like, it doesn't make sense to have any sort of cause and effect relationship there. So it's just an association. It just means these two things they happen together. So, and you can think about lots of reasons why. We're not going to go into that, but if you want to think about it, feel free. What about daily exercise improves mental performance? So this is both causation and association. So you can change the amount of daily exercise that somebody gets, and it turns out that will have a positive impact on certain measurable areas of mental performance. So because it's a cause and effect relationship, or a causation relationship, it automatically is both causation and association. You cannot have causation without also having an association. So a causation is a special kind of association. So both of the first two bullets there are both association, but only the second one is causation. What about the last one? Among college students, no link found between number of friends on social networking websites and size of the university. Well, it's saying that there's no link. So no link means no association. No association means no causation, so it's neither. So this is actually a really important skill to be able to have in a class like this, is to be able to read a headline or read the answer to a statistical question and understand whether association, causation, or neither is being implied by the study. So here's some things you can do to look for possible causation. So some keywords and phrases indicate causation. So I listed as many as I could think of. Causes, affects, implies, leads to, increases, decreases, influences, alters, changes, improves, due to, because, since, and if. Those are all words that basically whatever comes right before or right after that is a causation, right? Other keywords and phrases indicate effects. And so if you have an effect, then something has to cause that. So if you see consequently, that means something caused that to happen. Or as a result, blah, 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 that means something caused that result. So and therefore are also effect words, and therefore they're cause words. Now, some other keywords do not necessarily imply causation, but they might imply association. So, of course, the word association implies association. We also have before, after, connection, relationship, correlation, linked to, more likely or less likely. So if you see any of those words in a summary of a study or a headline, then causation is not necessarily implied. It still could be implied, but we're not being told just from the headline that it's implied. Right? So again, there is a association between height and weight. Right? There's also a correlation. They're also linked, right? So just look for these special words, and that'll tell you that you cannot conclude causation if these are the only words you see. And so before attempting to determine whether a study is indicating causation, ask yourself the purple question. Does this result necessarily follow from the proposed cause? Right? So you might see something like, well, we saw one in an earlier PowerPoint, and we're going to see it actually here in a little bit again, that there was that study in the 20-year study for the smoking females in the UK, and there was, turned out, an association between smoking and dying before the 20-year period is ended. But that was just a link. That was just an association. There was nothing in the study that said that there was a causal relationship. Or if there is one, that study couldn't show it. That's what's important. All right, next up, confounding variables, sometimes called lurking variables. It's a third variable that is associated with both the explanatory variable and the response variable. A confounding variable can offer a plausible explanation for an association between two variables of interest. And so we have a question at the bottom. Increased ice cream sales have been linked to more deaths by drowning. Are people more likely to drown if they have been eating ice cream? So let's just break this all the way down, and then I'll let you think about it some more. So look at the variables here, right? Ice cream sales is a variable. Death by drowning is a value of a variable, right? You'd look at a whole bunch of people. Some of them died by drowning, other ones didn't, right? We're taking everybody who could also be involved in eating ice cream and looking at whether they died by drowning or not. And it turns out that there is a link. So look, it says linked to, that's an association. That means ice cream sales and drowning are more likely to be found together. Is that the same thing as saying that people are more likely to drown if they've been eating ice cream? So if you're just looking at the keywords, linked to is an association keyword, right? Right here, right? This is just an association. And the other keyword here is if, right? If is a causation keyword. So can we take an association and turn it into a causation? Well, if you're not sure, just think about, does this make sense? Because this is a true fact. It is factually correct that in areas of the country or cities or whatever that have higher ice cream sales, more people drown there. So what do you think? What would a third variable be that might explain increased ice cream sales and drowning? What other variable, what other measurable quantity in an area, in a region where people eat ice cream and drown, potentially drown? So think about that. That's a discussion question. You can talk to me about that during class, or you can post on the discussion forum if you have ideas about this. But I want you to think about it. Oh, one thing before we move on from confounding variables. You are not going to be required to come up with confounding variables in this class. We're simply defining the term, so if I say such and such is a confounding variable, you know what it means. You are not required to read a study and go, aha, I can figure out a confounding variable for this. You don't have to do that, because it's generally too hard. But you should know what one is, right? So if I give you a study and it has 3 variables, one of them is the response variable, one's the explanatory, the other one would be the confounding variable. All right, now let's talk about types of studies. So there's 2 main types of studies, an observational study or an experiment. An experiment is a study in which the researcher actively controls one or more of the explanatory variables. An observational study is a study in which the researcher does not actively control the value of any variable, but simply observes the values as they naturally exist. So every study that exists in the world is either an experiment, an observational study, or a combination of these 2 things. Because the researcher either manipulates and intentionally modifies something in the study, or the researcher doesn't do that, right? So every study that has been assembled and carried out by researchers either has researchers meddling or leaving everything alone. That's the only distinction you need to know in this class. So experiment means the researcher actively controls something about the explanatory variable. Observational study, the researcher can do things, but just can't actively control the variables. Okay, so we saw this example in an earlier slide, earlier video. Do weightlifting exercises improve runners' 5-kilometer race times? So here is the full breakdown of how we would do this study. And this turns out this is a real study. It's a 2009 study. 28 runners were randomly divided into 2 groups. During the 6-week experiment, both groups continued their normal training routines, but only one of the groups was also given a set of 5 weightlifting exercises to be performed 4 times a week. So you're told this is an experiment, but what makes it an experiment? Well, the reason it's an experiment is that the researchers took the participants, broke them into 2 groups, and one of the groups got a different training routine than the other group. That training routine was randomly assigned, which you need to have, as it turns out. The treatment was randomly assigned, and it was manipulated by the researchers. They said, we have to tell this one group, here, you get these exercises, and then we'll see through collecting data if it improves the runner's race times, right? That's the idea. So it's a randomized experiment, so the study may provide evidence to show that lifting weights makes runners faster compared to those who do not. right? So we've already saw this example earlier in an earlier video, where we already know, what the variables are, the explanatory, response, categorical, quantitative. We already know all that stuff. But now we're tacking on this other idea of an experiment. So if the runners who lift weights get faster, then that would be a causal relationship. So we would be able to say, from a cause and effect standpoint, that lifting weights caused the runners to get faster. If indeed that's what the data shows. We are not looking at the data, we're just looking at what this study could show, right? We're going to look at the data in chapter 2 for stuff. And then here's this example again, right? This is another one we saw earlier. Is there an association between smoking and survival rates over a 20-year period for women in the UK? So here, this was a 1973 study. 1,314 women in the UK were asked whether they smoked. 20 years later, a follow-up survey observed whether each woman was deceased or still alive. So here you can see that the researchers simply observe whatever these women are normally or naturally doing. They have not manipulated anything. They have not broken the women up into groups and then assigned any sort of variables. This is just however these people are living, and they're observing the behavior. So that makes this an observational study. So this study is not capable of showing that smoking causes women to die within 20 years at a higher rate. Even though it might be true that smoking does cause that, this study was not capable of showing it because this study was not able to manipulate the explanatory variable, which was smoking or not. In fact, as you can probably guess, there has never been a study conducted on humans that was an experiment that showed smoking causes people to suffer any sort of ill effects. All of those studies have to be observational because you can't assign people to groups and tell them to smoke and then see what happens to them. You're just ethically not allowed to do that. And in the way old days, 1950s and before, that kind of stuff did happen, but the results of those studies are not used because it was conducted unethically. So there you go. That's observational study, and the other one was an experiment. Observational studies cannot show any sort of cause and effect relationship. Experiments can, depending on what the data shows. And so that gives us this big red sign here. Observational studies can almost never be used to establish causality. It is nearly impossible to avoid confounding variables in observational studies. In example 3, there could be many reasons why someone dies during a 20-year time period. The study can only show that smoking caused the increased death rate if smoking was randomly assigned to a group of participants in the study. And obviously, that can't be done. So here's your problem, right? Observational studies have confounding variables, like increased ice cream sales and drowning. There is some variable that's causing both of those things to happen. What if there's something that causes people to smoke and causes them to die earlier, right? What if it's a body chemistry thing? Or just the way that those people live might cause them to smoke. Maybe they're stressed out, so they smoke, and they're stressed out, so they die younger. Until experiments are done, causation cannot be established. And that leads us to the next slide, which is randomized experiments. So in our randomized experiments, the value of the explanatory variable for each unit is assigned randomly before the response variable is measured. If a randomized experiment yields an association between the two variables, we can establish a causal relationship. Only a randomized experiment can show causality. So there are experiments that are non-random, but they are not able to show a cause and effect relationship. So how does this work? Well, randomly assigning subjects to treatment groups, like with the weightlifting runners, prevents confounding variables from biasing the results. So let's stop and talk about this. When we looked at the study with the runners who lifted weights, those groups needed to be randomly assigned. If you assigned the runners to the weightlifting group or the other group using any other method, it's possible that a confounding variable could bias the results. So just think of any other way you can assign people to groups, and you can think of a bias. What if you took volunteers, right? So you have a bunch of runners, and you need 14 of them to lift weights. And you just pick the first 14 volunteers. Well, it's probably likely that the runners who volunteer to lift weights probably have a history of lifting weights, so there's something special about those people. What if you just took the first 14 people that signed up for the experiment? Right? So 28 people are in line for your experiment, and the first 14, you put them in the weightlifting group. There could be confounding variables there. What if people who arrive early, to get a better seat or to get a better parking spot or whatever, what if those people naturally respond better to weightlifting treatments because maybe they have a higher metabolism or they're early risers? We don't know. So the only way to get away from these confounding variables is just randomly assign everything. And as we saw before, we can randomly assign treatment groups with our calculators. So the randomization evenly distributes the values of all variables except the ones assigned by researchers. It doesn't mean it's a perfect system, but the idea is that you don't want confounding variables just popping up naturally. If there is a difference in the measured quantities between the different treatment groups, then the researchers can show these differences were caused by the different treatments. So that's how it works. What if an experiment is not random? So it turns out we've actually discussed two types of randomness now, right? We had random sampling, and then there's randomly assigning values of the variable by splitting the volunteers into groups. So let's think about the runners who lift weights again. Was that group randomly sampled? We don't know. But here's the thing, even if the group is not randomly sampled, we can still pick a population to generalize the results to that is acceptable. So even if those runners for the experiment are volunteers, that's okay. And that's what happens here, right? If the sample is not randomly selected, and when you're dealing with people, it's hard to get a random selection of people. Right? So a perfectly random sample allows you to generalize to the population. That's what we saw in an earlier video when I wanted to select 5 students at random from a class of 20. If I took data from those 5 students, I could generalize it in some sense to the entire class because it's randomly sampled. But what if the sample's not randomly selected? So if you're doing a study on runners who lift weights, you need volunteers. You can't force people to do a 6-week training program. This just means you can't generalize from the sample to the population. But here's the thing. By randomly assigning the variable, it allows us to draw conclusions as long as we pick an appropriate population. So even if your population is all runners who volunteer for studies, if we can show that lifting weights improves their times, then that's okay. That's okay that the population isn't all runners in the world or all runners in the United States. Okay, so this is our sampling bias. In experiments on humans, whether medical or psychological experiments on humans, or even physical fitness experiments, you need volunteers. And so you need this to happen. You need random assignment of the variable. So when you get your volunteers, you randomly split them into groups, and that allows you to make conclusions about causality. Even if you might not be able to generalize to the population you originally wanted, it's okay, because you can't force people to do experiments without them volunteering, essentially, right? Now, if your explanatory variable is not randomly assigned, so if you take volunteers to be in the weightlifting group, I mean, these are already volunteers who participate in the study, and then you say, who wants to be in the weightlifting group? Then it no longer becomes an experiment. Because as a researcher, there's no active assigning of a variable. You're just observing people as they naturally might be. So you cannot make causation conclusions. So this slide is pretty complicated, but I want you to think about it because there's two kinds of randomness. Random sampling and random assignment of the groups. In experiments on humans, it's okay if your participants are volunteers, but you need to randomly assign the variables. If you're doing random sampling without random assignment, then it's absolutely critical that you have random selection. Okay, so in an observational study, you still need random selection from the population. So it turns out that there are two kinds of randomized experiments. We will talk about both of these quite a bit over the course of the semester. The first one is called a randomized comparative experiment, and that's where we randomly assign cases to different treatment groups and compare the results on the response variable. So the runners who lift weights example, that is a randomized comparative experiment. So volunteers randomly assigned to groups, results compared. So you let them train for 6 weeks. Did the runners who lifted weights have a better improvement in their race times? Then there's another kind of experiment called a matched pairs experiment. This is a little bit different. When we do a matched pairs experiment, each case, so every subject, gets both treatments in a random order, or cases get paired up in some other obvious way, and we examine individual differences in the response variable between the two treatments. So these are actually very similar in a lot of ways, but the way that you look at the data is quite different. And we're going to see both kinds of these this semester. So a matched pairs experiment would be, these are done a lot in short-term psychological studies and very short-term medical studies. The example I'm going to show you is, it's like a human health science study, and we're going to see how to do a comparative experiment and a matched pairs experiment. Once you see it as an example, I think it makes more sense. So we're going to design a randomized experiment to address whether alcohol increases reaction time for each situation described below. The participants are 40 college seniors, so we're assuming everybody's old enough to drink, and again, you have to have volunteers, right? You can't force people to drink alcohol if they don't want to. And the response variable is time to react to an image on a screen after drinking either alcohol or water. So how could we design an experiment with two groups getting separate treatments? So you bring 40 people in, create two groups out of those 40 people, half of them get alcohol, half of them get water, and then a matched pairs experiment, which is very similar. We're going to have 40 people, split them into two groups, but in the matched pairs experiment, the two groups get both treatments, but in a random order. So that's going to be interesting. All right, so we have 40 college seniors. We need to split them into two groups. How should I do that? Right? For both a randomized comparative experiment and a matched pairs experiment, the first steps are the same. First thing we have to do is create two groups. So how are we going to do it? Well, we're going to use our trusty calculator, right? You can go into that random integer function and tell your calculator to select 20 random numbers between 1 and 40. Or, I mean, you can do whatever you want. You can do odd, even, because you're splitting things in half, as long as it's random, right? So you could have your calculator, select, 40 numbers, just either zeros or ones, and just assign 0, you're in the alcohol group, 1, you're in the water group. And just because it's random, it's a representative selection. The random splitting will allow you to draw cause and effect relationships. So this is the way I said to do it. Find 40 suitable volunteers. They have to be volunteers. Assign each one a number between 1 and 40. Use a random number generator, calculator, web app, or pre-generated list to create a list of random numbers between 1 and 40. Subjects given the first 20 random numbers in the list are assigned to group 1, and the other 20 will be assigned to group 2. So that's the way I said to do it. Just take the numbers 1 through 40 and mix them up, basically. So you can pull numbers out of a hat, because it's a small group, right? You don't have to use a random number generator. You could use ping pong balls or something, but there's web apps for this, and there's pre-generated lists for this stuff too on the internet. So you have your two groups, and so in a randomized comparative experiment, we need to assign the alcohol group to drink a certain amount of alcohol in a certain time period. So you have to figure out how long do you want them to drink for, and how much do you want them to drink. So the solution that you're going to see is actually something one of my students came up with a couple of years ago. This was an in-class discussion, and obviously something like this works better as an in-class discussion. And this fellow in my class came up with pretty much what I'm going to show you word for word. I remember when we were talking about it, I said, I'm going to use this for all future classes. So he said, group 1 will drink 4 12-ounce White Claw hard seltzers in 1 hour. So I don't know if any of you guys have ever drank alcohol, but that's actually not a small amount of alcohol in 1 hour. So it will have some sort of effect on some of the volunteers. So that's what you want when you do a study like this. Group 2, the water group, will drink 4 12-ounce ordinary seltzer waters in 1 hour. So think about it. These two groups are very similar. Both groups are drinking the same amount of liquid in the same time period. Both are fizzy drinks that look like water. The only difference might be a little bit of flavor and the alcohol itself. So the White Claws are 5% alcohol. Then sit all the participants, whether they've drunk the hard seltzers or the ordinary seltzer waters, put them in front of a screen and record how long it takes them to react to an image on the screen. So the details of that, I'll leave that to your imagination. It's really not important how you do that. But you would have somebody recording it, maybe on a camera, and then go back and measure the time it takes to react to the images on the screen, and then you compute the average reaction time for both groups. If the difference in the average reaction time is much larger for the alcohol group compared to water, then this will provide strong evidence that alcohol slows reaction time in the general population as well. And that's how statistics works, and that's what we're going to do starting in chapter 2 through the whole rest of the class. Will look like the data collection part of something like this. Right? In chapter 1, we just talk about all of the design elements, right? So this, to actually do an experiment like this would not be hard to do, but it has to be planned out well in advance. So that was the randomized comparative experiment, right? 2 different groups, randomly assigned, 2 different treatments, right? One is the actual alcohol treatment, we call it a treatment, and the other group is a comparison group. Measure the reaction time, and then take the average reaction time of both groups and look, is it a big difference in the average reaction time? A matched pairs experiment is almost the same, except both groups have to get both treatments in a random order. Well, we've already randomly assigned the groups, so all you have to do is bring everybody back the next day and switch the drink assignments and have everybody do the experiment again. Right? So a matched pairs experiment is really just a comparative experiment done twice. Right? What makes a matched pairs experiment different is how the data is collected and computed. So after the groups have consumed their drinks and taken the reaction time test, the experiment is repeated the next day with the group drink assignments reversed. The reaction times are recorded again, and the differences in the reaction times, alcohol minus water, for each participant are computed. That's not the same thing that we did in Part A. In Part A, we had two different groups and computed the averages for both groups. Here, everybody in the study has had alcohol and water. So we look at, for each participant, how much slower was the reaction time. So we only have really one set of numbers instead of two sets of numbers. And in most cases, we'd rather have one set of numbers. So even though this version of this experiment is harder to do because you need participants who are willing to come back a day later to do the thing again, the results might be more conclusive. If the average difference in reaction times between alcohol and water is large, then this will provide strong evidence that alcohol slows reaction time in the general population as well. So what we like about matched pairs experiments is that if somebody has a naturally slow reaction time, it's not messing up. Let's say one of the people in the study is just very, very slow. And that happens. Some people have slow reactions. If you do a comparative experiment and that slow person ends up in the alcohol group, then your data is going to be a little bit messed up because it looks like the alcohol caused this particular individual to be slow, when in fact that might not be true. In a matched pairs experiment, because you're measuring each individual person's difference in reaction times, if this particular person is very slow, the difference in the reaction time would still be the same as a regular person. And so that's the advantage. So whenever there's large differences in a population, these randomized comparative experiments are indeed better. Let's keep going. It's a long section, sorry guys. So there are 3 other features of good experiments. All experiments must be planned out well in advance so the correct inferences can be drawn. And we just saw how to plan an experiment, again, mostly based on one of my former students' discussion in class. But I thought it was a really good design. But you can see just how much planning that would take, right? It turns out there's 3 more important qualities you should look for in a good experiment: control groups, placebos, and blinding. So the control group is a good comparison for the group that got the treatment of interest. In our previous example, the non-alcoholic seltzer water is a good control because it closely resembles the White Claw. So again, you want to pick something in an experiment that is close. It doesn't have to be exactly identical, but you want it to just be close. You want it to be a good comparison group. Control groups are usually required for medical and psychological experiments. However, not all types of experiments need a control group. For example, if you want to test a marketing strategy using 2 different websites, you could just compare them to each other. So in marketing, and really a lot of business that experiments are done, you can just cast a very wide net and just do a whole bunch of comparisons. You don't need a control group marketing strategy. Like, that doesn't make sense. But psychological and medical experiments, you definitely need a control group. Now we have the placebo effect. So a placebo is a fake pill or treatment, and placebos are often used to control for the placebo effect in experiments. In many experimental studies, the placebo appears to be identical to the active treatment, but contains none of the active ingredients. So like our White Claw and seltzer water, right? That you might think of that as a placebo because people drinking it, you put some lime juice in it or something, people think that they're getting White Claw. Maybe that's a psychological thing and it makes them act different. When people believe they're getting an effective treatment, they may experience the desired effect, called the placebo effect, regardless of whether the treatment is any good. This has been known for a long time. People have known about the placebo effect probably for 50 or 60 years, but it wasn't until about 30 years ago that researchers realized just how serious the placebo effect is. And that's what we're going to see in our next example. Blinding. In a single blind experiment, the participants are not told which group they're in, treatment or placebo. So that would be good for the alcohol and reaction time experiment. Having it single blind would be very, very good. Don't tell people which group they're in and see if they act different. In a double-blind experiment, the participants are not told which group they're in, and the people interacting with the participants and recording the results of the response variable also do not know who is in which group. So it's hard to see why a double-blind experiment would be necessary. But if you're trying to learn something about human behavior, especially psychology, or human medicine, there are many hidden things, unconscious things going on that you might not notice. So you should always just be careful and be safe and do a double-blind experiment so that there's no biases that creep in without your knowledge. So let's see an example of this. So this example, this is a real study, obviously, and I have a link on the next slide to the follow-up study, which is even, in a way, more shocking than this one. So if you guys haven't seen what I'm about to show you before, it's hard to believe that it's true. But that's why we have to do studies, because of things like the placebo effect. For people suffering from arthritis of the knee, arthroscopic surgery has been one possible treatment. In the mid-1990s, a study was conducted in which 10 male volunteers with arthritic knees were scheduled for surgery. They were all treated the same except for one key difference. Only some of them had the real surgery. Now think about that. The researcher, who was a surgeon, figured out that if I give people a fake knee surgery, maybe they'll get better because they just thought they had a real knee surgery. And what do you think happened? Once each patient was in the operating room and anesthetized, the surgeon looked at a randomly generated code indicating whether he should do the full surgery or just make 3 small incisions in the knee and stitch up the patient to leave a scar. All patients received the same post-operative care, rehabilitation, and were later evaluated by staff who didn't know which treatment they had. The result? The men who got the sham knee surgery and the men who got the real knee surgery showed similar and indistinguishable levels of improvement. This is not a new phenomenon, but it just seems like it can't be true unless you start really thinking about it. So let's break this thing down. Let's answer questions A through D, and then that'll be the end of the slideshow. So how is randomization used? Remember, this is an experiment, so we need to have randomization. How is a placebo used? It's a good experiment, so it needs to have, and it's a medical study, so it needs to have a placebo. Is the study double-blind? So again, medical study with placebo needs to be at least single-blind, but should be double-blind. And what do the results of this study suggest about real surgeries as a treatment for arthritis? So let's just talk about these. The answers are on the next slide, but let's just talk about them. So randomization, the surgeon looked at a randomly generated code, which was probably generated by a calculator, computer, or an app. And that was all set up ahead of time, probably sealed up. The patient is wheeled in, and then the sealed envelope is opened. Real knee surgery, it's a code, because if somebody sees it, you don't want them to know what it was, but real knee surgery or fake knee surgery. So randomly selected treatments for 5 of the individuals. How is a placebo used? So this one's a little tougher. So let's look. Do you guys see a placebo here? Right? So the idea is the placebo is actually the 3 small incisions in the knee. Because the patient doesn't know if they're getting a real knee surgery or they're just getting randomly sliced up. They don't know. So that's your placebo. It's kind of hard to find, but that's a placebo, right? The fake knee surgery where those incisions are made. Is the study double blind? Well, we know it's at least single blind because it has a placebo. But it turns out it is double blind as well, right? It's right here. The staff who did all the post-operative care and rehab did not know who had real knee surgery and who didn't, because the physical therapist might treat people, if they knew that they had a fake knee surgery, they might treat those people differently. And you don't want that. So nobody knew. Only the surgeon and the researcher, the designers of the study, knew who was in which group. And they didn't interact with the patients until the study had come to a conclusion. And what do the results of this study suggest about real knee surgeries as a treatment for arthritis? Well, based on what we talked about, it's pretty clear that real knee surgeries might not be needed. So this is a landmark study, right? And so the follow-up study was done in 2002. There's a link here to it. It's New York Times article on it. It's really, really good. Obviously, I don't have time. This is already going to be a very long video. I don't have time to go over it, but if you guys are interested in this sort of thing, or if you want to go into physical therapy, occupational therapy, or any medical, so nursing, pre-med, any of that kind of stuff, you should actually read this study with the link. It's very, very interesting, and it's very, very cool. So you guys think about this example. You're probably going to have questions about it. We can talk about this during our class meetings if you want to. Or post a comment on the discussion board about this, because this should be surprising, these results. But this is how it works, and this is why studies have to be done the way they are, and why data has to be collected the way it is. All right, well, that's the end. Here's some concepts to remember, and here is some extra practice if you guys need extra practice. All right, well, that's the end of chapter 1. So the next video you see will be, Katie Dobeck posted a video, how to do the adaptive practice quizzes. So that'll be the next video that you guys watch. If you want to work ahead and start on chapter 2, that's fine as well. I'll have those videos up by the end of the week. All right, guys, thanks a lot, and see you in class. Bye-bye now.